database systems, storage part 2. Last time, the last thing we talked about was nested RAID, and I added a couple of slides for today because there seems to be some confusion on what hard disks can or cannot do. And the bottom message here, the bottom line is hard disks are awesome. You will see it's like a mini computer, basically. So one thing is related to fault tolerance. So when you look at a hard disk, there's a smallest unit of data that you can refer to on a hard disk. It's not a byte, but something bigger, and that's called a sector, a hard disk sector. That's a unit for read and write access that we can use on a hard disk. We can't read less than such a sector. So it's typically 512, but up to 4K kilobytes. That's the size of such a sector. And the interesting thing is the stuff is stored with error correction codes. So to a certain degree, the hard disk is able to fix problems on the device. Yeah? So whenever the hard disk reads data from the platter, it will run that data through an ECC algorithm and find out whether there was a problem. And if the problem isn't too big, the hard disk will be able to correct those problems. Yeah? So this is important for RAID to understand. You don't need a RAID system to fix the simple problems. RAID will be useful when fixing the big problems. Yeah? That's the important thing to understand here. Yeah, so the details are in those articles. So this is a really insanely detailed article. I invite you. You don't have to read them if you want to. I mean, you will understand the many abstractions we are using in that lecture to make the stuff digestible. Actually, things are way more complicated than how we explain it here. So one confusion that's always present when talking about hard disks is sectors, hard disk sectors and operating system blocks. So as I told you on the previous slide, there's a hard disk sector that's 512 bytes to 4 kilobytes, and then there's a block. And a block typically contains multiple sectors. So when we talk about a block, be it in an operating system or in particular here in the database class, that's something bigger. So a block contains multiple of those sectors. To make it more complex, when you read and more confusing, when you read about hard disks, you will find out that people, when they say sector, they actually mean a block. It's very confusing. Yeah? So block may mean a hard disk sector, or it may mean a database block, also known as a page. Very confusing, I understand, but that's the kind of terminology that's unfortunately being used. And what we talked about in the previous lecture and in the previous lab was how to get data from the disk. And I told you about, okay, there are different platters, and then there's a seek operation, you move the disk arm, and so forth, and so forth. However, that is not how the interface on a hard disk actually works. So we learned already we have cylinders, we have head, and we have sectors. Yeah, so if you know the cylinder, if you know the head, meaning the right side of the platter, and the sector, it's a unique address of a sector on such a device. Yeah? So that could be the address you send to the device to retrieve any data or to write any data to that device. So that's called a logical CHS number, cylinder head sector number. And that could in principle be used, and that was used a long time ago. However, that got also translated, was split into physical and logical CHS numbers. So the device had a physical layout. It had a certain numbers of cylinders, of heads and sectors, but to the outside, the devices were mimicking a logical, something completely different, a different number of cylinders, a different number of heads and sectors. So it was remapped inside that device and was very confusing. This is not used anymore. Today what is used is logical block addressing. And that's a bit like if you create a relation in a database system, you have these auto ID fields. They're just an integer numbering from 0 to whatever. And that's basically the same thing here. So how you address a device is something like that. You say, okay, give me the block 42, 42, 42. And then there's a mini computer called the hard disk controller inside that device that will translate that to the right CHS physical address on that disk, and will do the things that are necessary to retrieve the data or write data to that right position. Yeah, so you don't have real influence on, you can't say I want to write to this cylinder or to that head and so forth. It's all hidden by this translation logic. And that has some it has some downsides, and it has also some advantages. One advantage is that the device can remap bad sectors. So if you do a get block 42, 42, 42, and send that to the hard disk controller, it may retrieve that block from this CHS address, but it may also retrieve it from that CHS address. Yeah? So it may come from a different position on that disk, depending on where the HD controller decided to put that data. This allows the device to remap data without telling that to the outside. This is done in the factory already. So before the device is delivered to you, they will check the quality of the sectors. Do they receive many errors, yes or no? And if they receive many or too many errors, what they will do is they will mark the sector as a bad sector and remap that sector to a different position on the disk. Yeah? So if a sector doesn't work on such a device, it doesn't mean that the entire device can't be used anymore. They still ship it. They just hide the errors by using this remapping mechanism. Yeah, that's a nice feature, in particular for the vendor, but it may be a problem for what exactly? Any idea? And I was just told that I can throw this in the audience. This is super soft. I won't hurt anyone. So if you want to answer any question. So why could that be a problem for a database system if too many blocks get remapped? By the hard disk controller, we have no control on that. Any idea? Yo! The guy behind you. Thanks.
We might not be able to do real sequential reading.
Yes. Yes, exactly. We believe, I mean, we don't have an interface to say sequential read. We just retrieve these blocks, and we can make an assumption that, okay, if I retrieve block 1, 2, 3, 4, 5, 6, 7, it's probably a sequential kind of access pattern. However, if there's a lot of remapping in between, rather than doing efficient sequential scans, there may be a lot of disk arm movements in between. Right, that's exactly right. So this HD controller does many things. Among others, it can also optimize the access patterns. So if you if you send many requests to the controller, like blocks with very different addresses, logical block addresses, yeah, and maybe the disk arm would have to go like this, the controller will reorder those requests into what's called an elevator pattern. Yeah? So remember, an elevator, when you go somewhere, it's not like one enters the elevator, goes to the 100th floor, and then leaves. It's really like the elevator will stop on the way to collect other people and then drop them when they reach the right floor. Yeah, that's the same here. Yeah? So the elevator will collect requests a little bit like in that circular scanner I explained the other day. Yeah? So it will try to optimize the movement, minimize the movement to answer multiple requests at the same time. Of course, there are limits to that. Yeah? You shouldn't wait too long to, yes, that's even faster. Okay, so that's what I just explained. So what that means is, so hard disks are awesome. They do many, many things we don't have to worry about anymore. So the interface is way more high level. A hard disk is basically a key block store. So you map a key, that is this ID, to a block of data. Yes?
But if there is a bad sector and we have data on it,
yeah.
We can remapping anyway because there is redundancy on the hard disk, or how does it work?
No, the redundancy is completely hidden. You don't see that stuff. It's a net sector and a gross sector. So you believe you store 512 bytes, if that's the sector size, but the hard disk keeps some extra information. Can be on the order of 10% more data that's stored somehow. You don't see the stuff.
So it's possible for the disk controller to remap the bad disk?
Yes, it can, yeah. There are two situations here. The one is the sector can retrieve the data and correct the data, but it feels like, oh, there are too many errors. I always have problems with that sector, so I rewrite the data to a different place. But there can also be the other situation that the data recovery is not possible. Yeah, so it's really, the sector doesn't work anymore. You can't retrieve the data anymore. And in that situation, the hard disk will signal, oh, there's a bad sector. I can't retrieve your data. And then RAID kicks in. Yeah, at that point in time, because you have to send the data again to that device, and then it will be mapped to a different place. Yeah, but there can be situations where you can't recover. Yeah.
Doesn't the bad sector reduce the capacity of
Yeah.
the hard disk?
Yeah, of course, it does reduce the capacity, but what I read is, I went through that in the past days, it was really interesting because it's in the domain of the hardware research community, kind of a different domain. But what they claim, what happens is when you get a device, they always, the device already has some spare sectors, yeah, that wouldn't diminish the total capacity. I don't know what that number is, but that's the idea. Of course, if you have too many bad sectors, eventually you will have a problem. Yeah? Yeah, anyway, if the fraction of bad sectors increases below a certain threshold, you better change that device anyway. Yeah? Okay, so this is like 2 centimeters on the iPad. It actually works. Okay, so it's this point. So, and that brings me to physical and virtual pages. So as I said multiple times already, the storage layers in the database system have very similar properties sometimes. And here, if you look at that interface, I mean, you want to have a block or a sector, as they call it, on a disk. From that disk, you give it an ID, and then the disk retrieves the ID. Have you seen that before in this lecture? And maybe it was last Wednesday. Anyone remembers? We had a very similar situation where we say we want to have this chunk of data. Yeah, if you remember the database buffer, what does it do? There's a get operation. You say I want to have page 42, and then the database buffer has to load it from persistent storage into main memory and returns the pointer to you such that you can access it. It's the same story here. Logical block addressing, as explained here. Give me that block, and of course that only this core will only return once the data has been retrieved from the platters and can be sent up in the storage hierarchy. So it's a very similar interface, and yeah, that's an interesting thing that happens on the storage device. It happens in the database buffer, but it also happens in the operating system through virtual memory management. Who of you knows about virtual memory management already? Oh wow, okay, that's interesting. Not so many. It's not so widely known. I learned about that when I studied like in the, I don't know, 5th semester many years ago, and then I forgot about it. And then I learned that this is actually super useful for database systems, and many interesting inventions have been made around virtual memory management. And again, it's the same idea. Yeah? The idea is you have an ID space somehow, a virtual memory address, and you map it to physical memory addresses. Yeah? The same as we just saw before with the disks. Yeah? So here we had the LBA, and we mapped it to CHS. That's what happens on the hard disk, and the same happens in main memory, and that is supported by the operating system and by hardware. And this is called virtual memory management, and it has many advantages. One being the process. Each process has a separate address space. The second is you can protect processes against each other. And there are many more advantages, but one is also that you can simulate a much larger main memory than actually available to the process. You can pretend, oh, I have 2 terabytes of main memory where there's only 1 gigabyte. That is all happening or possible with virtual memory management. Yeah, but the main idea is when you write a program and you have any pointers and you allocate stuff, that stuff will not be accessible for your program through a physical memory address, but rather through a virtual memory address. Yeah? And whenever you reference anything in main memory, that address first has to be translated somehow to the real physical address. That's called physical memory management, and is very useful. So we go back to that, but before going deeper into physical memory management, I'd like to explain a technique that was used before this virtual memory management was used in very old systems, but it's kind of, I mean, it's clear that there has to be something like that. And when you recall, in database systems, you always have the problem that we want to make sure that the database is consistent. Then the transaction comes in and screws up the data. And then if the transaction doesn't commit, we want to be able to go back to the old consistent state. It's very important in a database system. And one idea how to do that was used very long years ago is called shadow storage. And this idea, you will see that in computer science reappears over and over and over again under different names. The idea is really simple. The idea is you always keep an old consistent version of a page. And now when you want to change that page or number of pages, you create new, possibly inconsistent version of that page. However, you keep a second copy. So whenever you modify something, you first copy the old page to a new page and you do all the changes on the new page. And once you're done, you basically copy the new page over the old page and then you're back into a consistent state. It's not that you only have one copy of your data and you change it, and then if anything goes wrong, you're in trouble because you can't go back to the old state, to the old version. You do the change on the new state. A little bit like when you work on a file, maybe a pattern you will see often is, okay, you do a copy of the file and then you do the changes in that file, and eventually you decide you keep those changes or you throw them away. Then you go back to the old file. It's exactly the same idea here. But how this could be done in shadow storage is again through a mapping that hides the physical pages, the physical addresses of the pages. So how that works is shown here in this slide. So basically you have your physical pages in the middle. You have a pointer. It's just one bit pointing to what is currently the consistent version. That is called version A, or you might call it version 0, it doesn't matter, but that's my A version. And now if anyone wants to retrieve a particular page, it is not allowed to go directly to that list of physical pages, but you always must go through a mapping. So here's a mapping table that basically when you come in with a virtual address, like in the logical block addressing, give me page 42, that mapping here will return you the page. So the mapping may map that page anywhere on that list of physical pages. That's the idea. It's one indirection, making sure that you don't access physical addresses, physical pages, but all accesses will happen through that logical indirection. And then you can do things as follows. Assume you want to modify something. How do you modify something? You basically copy over the page table. That is what happened here. You copied MA to MB. You see this is exactly the same mapping as that mapping. So nothing happened so far. And important here to note that the pointer here still points to version A. So nothing changed in that regard. Now if a transaction wants to do modifications, changes data, insert, update, delete, whatever, it does all the changes through this page table B. That is the inconsistent version. So that may look as something like that. For instance, here you create a new page. So you want to change the page. So that was a page, if you look at the logical numbering here, yes, so 0, 1, 2, 3, 4, 0, 1, 2, 3. So that is logical page 3, this one, that in version A points to this physical page. In version B, it points to that physical page. So you copied over the old version of the page, do the changes in that page. However, at all times you preserve the consistent version A. That's unaffected. Just the pages that you change are copied to a new physical page. You fix mapping, and then you do the change through that mapping. Okay? And then there are two options. Either you commit or you abort. So here again, here you create a new page, change the mapping again, basically same as before. But now, oops, come on. What happens if you abort the transaction or the system crashes? All you need to do is to throw away that mapping underneath, and then you're back in the initial state. Everything is fine. You don't, if you abort the transaction or crash for any reason, Then the second case, if you want to commit, the only thing you need to do is to change this pointer. Yeah, meaning now the consistent version is version B. Okay. So what is that you have to do then? You have to copy over the contents of this page table to version A, because the next change, of course, the next incoming transaction will operate on version A. That will be the inconsistent version at that point in time. Yeah? So you swap roles. Yeah? At one point, A is consistent, B is inconsistent. Once the transaction on B was committed, you swap roles, that becomes consistent, and A is the inconsistent version, and so forth, and so forth. Is that clear? Yeah. Maybe you use a cube.
How can we handle race condition in this scenario?
Yeah, this is okay. That's a different story. That's kind of orthogonal. Here, I assume that all transactions come in a serial fashion. Yeah? That's a different story. We will handle that when we look at concurrency control. But it's a fair question. Yeah. Other questions? Yeah?
Does it allow us to not to have to use a lock for writing in repeatable reads?
A lock for writing? What's the question? Lock, you mean L-O-C-K or L-O-G?
So we saw in the last week exercises the varied type of transactions. So let's say we want to have repeatable reads.
So then it's an L-O-C-K, okay? Yeah.
A lock for writing, right? Because
Yeah.
we just copy the page. And
Yeah.
we need one for committing later.
Yeah.
Is it the case?
I'm not sure whether it's a question whether you can support isolation level repeatable read.
I mean, using the system, then we probably don't need a lock for writing. I mean, we don't need a lock for reading. So we have repeatable read, we have a transaction, one that reads a file, and then we have another transaction should have write the same point. If you have the system, you actually don't need a lock there, right? Or
Yeah, it depends on the log granule. And as I said before, for the moment, assume that transactions come in a queue, one after the other. In this situation, you don't need any locks, yeah, because there's no concurrency. It's just a serial. Yeah, once the transaction one has finished, the next is allowed to operate. Now, of course, you don't do that in a real system. Then you allow for concurrency, and then you have to think about how to organize those locks. Yeah, and then of course, then the question is, okay, if I have multiple transactions running at the same time, shouldn't that be multiple versions? Here it's only two, the consistent version and the inconsistent. But if you have n transactions that are currently ongoing, you have n different inconsistent versions. Yeah, so there's a different story behind that, but we will look at that. Yeah? So I'm just saying that's a very old and the most simple thing you can do to keep consistent and inconsistent versions without destroying your consistent version. Okay, so the advantage of that is you only double here the storage for the change pages, not for all of it. Yeah? Assume you could also keep two separate versions of the relation, yeah? The consistent and the inconsistent. Yeah? You will also copy over all of the stuff that's unchanged. That's not done here. Only the change pages are copied over. Undo is very easy. The helper data structures, these maps may become big because you need a mapping for each entry. Yeah? Depends on how you define big, but might be a problem. And what's also a problem is there might be a high degree of fragmentation. Fragmentation meaning, okay, that may trigger eventually random reads, so that's not so cool, at least if it's disks in your system. So an alternative to that is called a page table, and that is what your operating system uses. So again, when you use a pointer in your system to address some memory you allocated, then that memory has a virtual address. And how these pointers work is basically through a prefix mechanism. So prefix meaning you read the first portion of that address and ignore the remainder. So that in this example, this could mean that the first 32 bits get translated into these 32 bits. And this is basically then the page ID. So the logical page 32 gets translated to physical page 56. And what is this? Well, why didn't I translate the remaining stuff? I just translated a part of that address. Why is that? Yeah, maybe someone else? You should always make it that you can throw the cube as far as possible, right? So someone in the back seats. So why didn't I translate the second part of that address? Why did I only translate the orange here? Maybe that's an acceptable. No. Okay.
Because otherwise you will use just the full address to map the same address. So like, you get a point to save mapping memory, I guess.
Yeah, maybe you might mean the right thing, but I mean, what is this address about here? This is white digits.
It's the offset where you can validate the page.
Right, that's the offset inside the page. You don't have to touch that. It's just about the page ID. That is the first part of that. So depending on the page size defines the number of bits you find here, of course, if you want to address each and every byte in such a page. That will define the number of white bits, and this is the number of pages you have in your system. Okay, and how you organize that is basically through what we call a prefix tree. That also has a name, a prefix trie, or a radix tree. There are many different names for that. But the main idea is that you make a decision on how many bits, so basically you can map it to a tree, and then you make a decision on how many bits do you want to consider in each step. Yeah, if you start from the parent here, if that is your root node, and now you want to go down to the children nodes here, we have to make a decision, okay, how many bits should be mapped, should be represented by that node. And here I made the decision to map 2 bits. 2 bits means I have 4 different possibilities. So 2 bits can represent 4 numbers, 0, 1, 2, 3. So everything that starts with 3, like this guy here, goes in this subtree. Everything that starts with 0, 0 goes into this subtree. Okay, and then you recurse, of course. Then you can do something like that. So here I made the decision that the next level would represent 4 different bits, the blue bits here. Yeah, and then that means this guy here has 4 children. And so once you reach this one by following a 1, 0 prefix, yeah, that is what the 2 is about. Yeah, then you have to understand the next 4 bits. Yeah, so 0, 0, 0, 1 is this one, and so forth. Yeah? So basically, the prefix of the virtual address defines a path in that radix tree, in that prefix tree. Yeah? You take one chunk of bits here, yeah, that helps you to understand, okay, what is the first child I have to go to? That's this one. You look at the next one, gives you the next child you go to, and so forth and so forth. Yeah? So that's basically how you can map a virtual address directly to a physical address. And eventually down in the leaves, then there's a number pointing you to the physical address, and that will be used to replace, as we had seen here, to make that replacement here. Yeah? So eventually there's a number in the leaf of that tree telling you, okay, that's a physical address, and there you go. Okay. One thing that you will also see is, and that's related again to the shadow storage algorithm we saw before. It's called copy on write pattern, abbreviated as COW. There's also a database book that's called the COW book. I'm not sure whether it's related to the copy and write pattern, but if it has cows on top, I don't know. It's very old, actually, the book. Anyway, and what does a copy and write pattern do? So given some physical memory partitioned into units, we have that's pages, and then you have allocate, write, update operations on units. The idea is, do you hide the physical addresses, like in virtual memory, as shown before, like in LBA? You make users share the data without them even noticing. Yeah? And you copy physically, not only at allocate, write, and update time. So what that means is, if you have a process in Unix, and then you fork the process into a child process, the child process will get a page table of its own. Yeah? So assume you have one process that has a lot of memory, allocate a lot of memory, and now you fork. You could assume, oh, now all the memory gets physically copied over, right? No, that's not what happens. What's copied over is a page table. Again, as in shadow paging here, that's basically this situation I'm currently explaining. Here, yeah, so you're here, now you do a fork on a process in Unix, which means the page table, yeah, now I say this is a page table here, gets copied over, and now if that child process or the parent process wants to change a page, you have potentially the problem, if you do that, both would see that change, right? You don't want to do that because you want to keep this, two different processes apart. So you do the same as in shadow storage. What you do in this situation is, and I showed it already here in using the name shadow storage, is the second, let's assume this process that has this page table, wants to modify this page here, has to copy it over to a new page, change that entry in the page table, and then do the change. This is called copy on write. Only when you want to write to a page, when you change a page, you copy it over. You copy the read-only version over to a new physical page, change the rewiring, and then you do the change. That has the advantage that this process here, using that page table, doesn't see this stuff. It's completely unaffected by the change of the second process, and vice versa. Yeah? So now what happens if you want to change this again? Do you copy it over, yes or no? Maybe someone else. So did you get the copy on write idea? Yeah? But, or should I explain it again? Maybe here again, maybe the blue. Oh, you have it, you still have it. Oh, that's not valid, right?
But like when you're doing the copy on write, are you actually creating a new entry in the page table?
No, you rewire because, I mean, if you go back to the situation, that is, once you fork the two processes, they have the same page table, they have the same entries. So the logical, the virtual addresses point to the same physical pages. Now you see that here. Basically imagine, this is a mirror basically currently. Yeah, all the arrows point to the same physical pages if you go through the mirrors. Yeah, so they see the same data, no change whatsoever. Now one of them, it doesn't matter who, wants to do a change. If I didn't do anything about that, this would mean if I now directly wrote here, whatever something, both would see the change. That's not what you want. You want to make sure that only the changing process, this one, sees the change and the old process sees the old data. Yeah? So what do? You copy this page over to a new page here. Yeah, you see that on the next slide, that happened here. That's a new version of this page. And now the change will be done through that rewired entry. So now this virtual address here in the page table doesn't point here anymore, but it points here. Completely transparent to the process. So the process at all times here uses the same virtual memory address to address that piece of data. Yeah, you don't have to inform it or here's a new address or stuff like that. No, it's the same address. Yeah? But what the operating system does underneath is this copy and write operation. It understands, oh yeah, that's a shared page. Multiple processes see that. I create a copy for this particular process, and then that process can do whatever it wants on that page. That's what's happening here. Yeah, that's called copy on write. And yeah, but now what happens if you want to change it again? Yeah, assume this process that created that page 6 wants to change that page again. What happens? Yeah, maybe there's someone in back row. That's a funny thing. We should get that for uni.
I think it depends on what you want to do. If it's the only process that's accessing data, I think it's just change again. And if we have multiple processes, we do another copy.
Yeah, the idea of copy on write is really to own the data. So the process gets its own private copy, so to say, which by definition means only that process sees the data. And then you're right, you just change the page. There's no need to do another copy on write again. Okay, here's another question. What happens if I change this page such that the contents are equal to this page again? And now it's your turn, but first we need it here.
Could we just change the pointing arrow instead of just having the same data twice?
Yes, exactly. You could do the inverse of copy on write, that is called merge on write, and as far as I know, operating systems don't do that. But that's also called deduplication. Yeah, you have. Yeah, but first things first. So if you're in the situation that the change here in that process is like that the contents of this page are not the same as that one, there's no need to keep the separate copies. So you could actually kill that arrow and make it point there again. Yeah, but then you would first have to detect that. However, this operation is called a common problem. If you organize large data sets and they overlap to a certain degree, then you want to deduplicate the data. You want to identify portions of the data that are equal, and then you do a similar technique, yeah? Because you have to keep pages only once, not multiple times. Okay, cool. Yeah, that's basically it for yeah, so this copy and write pattern, that's where we were. So it saves considerable storage space. You have mentioning overhead for page tables, however, it's a good trade-off. You have some fragmentation, but it's typically not that severe. And similar ideas are, again, used all over the place, not only in databases. Shadow storage, I showed you. Virtual memory is all over the place, like any device uses that. File systems do similar things. Versioning systems do similar things. Always the same idea. Okay, and to wrap the storage portion up, so basically, again, we looked so far at this stuff here. Yeah, that's the storage hierarchy. But yeah, if you think about what is the internet, it's just a bunch of other storage layers. It's the same thing again. Yeah, okay, this is separate people doing that in research, network, internet research. But from the point of view of a database system, it's just a bunch of other storage layers. They may have different constants. So it may be that, if I retrieve some data from Frankfurt, maybe that's, I don't know, 5 to 10 milliseconds, versus Iceland, maybe it's 20 milliseconds, I don't know how long it takes. And the US is probably, I don't know, 50 milliseconds, no idea how long the satellite takes. Yeah, so it's just a game with those constants. But conceptually, from a very high level, it's the same ideas. Yeah? All of that is a huge storage hierarchy. And for you, important to keep in mind is there's no need whatsoever to invent separate technologies for each combination or each single storage layer. It will always be the same algorithms and the same techniques with different names to make life more complicated. Okay, yeah? But the core ideas you will see over and over again. If you understand what the database buffer does, you will understand caching across all layers. So you have a caching hierarchy for the internet, for instance. Yeah, these storage networks. Yeah, if you go to Netflix or Amazon Prime or something, it's not that you retrieve the data from the US. There's a huge hidden network of storage systems underneath, making sure that you retrieve your the newest James Bond movie not from the US, but from a data center in whatever, Kaiserslautern or Frankfurt in this case. Yeah? That's all hidden, but it's all about, it's the same thing as basically what the database buffer or any other caching mechanism does. So there are subtle differences and details, I understand, but high level, it's the same stuff. Okay, so in summary for the storage part, so the properties of the storage hierarchy impacts query processing efficiency. So what we see is it's all very similar across the layers. I just told you that. So we have to think about what are the read strategies, when do we read, what do we read when, caching strategies, what to keep on a layer, and until when, Caching is done in hardware versus software. So caching on certain levels is done in hardware like L1, L2 and so forth, whereas some is done in software like the database buffer. We have to think about write strategies. When do we write down data? We discussed that last Wednesday. There's a power failure, the data is only in memory, it's gone, so there must be an extra mechanism to make sure we don't lose the data. The main concern with I/O is this random versus sequential I/O trade-off. This is very prominent on hard disks, but exists similarly on other devices like SSDs and even in main memory to a certain degree. And we talked about these split layers. We talked about NUMA, so on the main memory level we have multiple different layers, multiple memory regions where we may have different access times, and the same holds for RAID and for the network, of course. Multiple hard disks or multiple servers on the network. Yeah, that's it about storage. Here are some links.